8.4 Coupled first order simultaneous differential equations. In some real-life situations, rates of change of two variables are connected. For example, in a predator-prey model, the rate of change of the population of bears might be dependent on both the number of bears and the number of fish in a river. Simultaneously, the rate of change of the number of fish might be dependent on both the number of bears and the number of fish. In this case, you have two dependent variables, the number of bears and fish, and one independent variable, time. You can set up two first order differential equations to model the rates of change of the numbers of bears and fish, and letting the numbers of bears at time t be x and the number of fish at time t be y. You can write dx over dt equals ax plus by plus some function of t, and you've also got dy over dy over dt equaling cx plus dy plus f of g. Now, if f of t and g of t are both 0, the system is said to be homogeneous. These equations are called coupled first order linear differential equations, and you can solve them simultaneously to find x and y as functions of t. You can solve coupled first order linear differential equations by eliminating one of the dependent variables to form a second order differential equation. Example number 12. At the start of the year 2010, a survey began on the number of bears and fish on a remote island in North Canada. After 2 years, the number of bears x and the number of fish y on the island are modelled by the differential equations dx over dt equals 0.3x plus 0.1y and dy over dt equals minus 0.1x plus 0.5y. And for part A, we have to show that d squared x over dt squared minus 0.8 dx over dt plus 0.16x equals 0. So to do this, you'll notice in this equation there's nothing involving a y. The only variables we're dealing with are x's and t's. So for part A, from this first equation we can multiply through by 10. So we have 10 dx over dt equals 3x plus y, and we can now rearrange for y. Y is equal to 10 times by dx over dt minus 3x. And now we can differentiate both sides with respect to t implicitly, and if we do that, we have dy over dt equaling 10 d squared x over dt squared minus 3 times by dx over dt. Now let's call this equation equation 3, and let's call this equation equation 4. So what we can now do is, over here, is substitute equation 2 and equation 3 into equation 4. We know what dy over dt is. That's this result over here. Obviously this one is in terms of x, and we also know what y is as well. That is over here. So we have 10 lots of d squared x over dt squared, and then we have minus 3 lots of dx over dt. This is equal to minus 0.1 x plus 0.5 y, and y is the result we have over here, 10 dx over dt minus 3x. So what we can do is tidy all this up. Hopefully we'll end up with what we have over here. So we've got 10 d squared x over dt squared minus 3 times by dx over dt minus equals minus 0.1x. Now 0.5 times by 10, that's 5, so we've got 5 dx over dt, and 0.5 times by 3, that's 1.5. So here we have minus 1.5x. And if we take everything over to the left hand side, you can see we end up with 10 d squared x over dt squared minus 8 times by dx over dt plus 1.6x equals 0. And now what we can do is divide both sides by 10, so we end up with d squared x over dt squared minus 0.8 dx over dt plus 0.16x equals 0. For part B of the question, we have to find the general solution for the number of bears on the island at time t. So bears is represented by x, so we need to find the general solution for x. And for this, we can first of all form the auxiliary equation. We have m squared minus 0.8m plus 0.16 equals 0. And we have m minus 0.4 all squared equals 0. M is equal to 0.4. So therefore, x is equal to a e to the 0.4 t plus b t to the power of bte lots of e to the 0.4 t. Okay, so that's how we do part B. For part C of the question, we have to find the general solution for the number of fish on the island at time t. So we need to find out what y is, and happily for us, we already know what y is over here, but for us to find out what y is, what we need to do is find out what dx over dt is, and also what x is. Well, we know x, we need to find dx over dt first. So if we take a look at what we have over here, for part C of the question, dx over dt, that's equal to, well, here we end up with 0.4 a e to the 0.4 t, and then through the product rule, we add on 0.4 bt e to the 0.4 t plus be to the 0.4 t. And now we will substitute these into equation number 3. So if I call this equation 5, we've got equation 6 here, and we've got equation 7 here. We're going to substitute in equation 6 and 7 into equation 3. So what we end up with is y equaling 10 lots of this result here, the 0.4 a e to the 0.4 t plus 0.4 bt to the 0.4 t plus be to the 0.4 t. Then we subtract off 3 lots of a e to the 0.4 t plus bt e to the 0.4t. And if we tidy all of this up, you can see y is equal to, well, we've got 10 lots of this, and what else do we have? Then we've got this result over here. So 10 times 0.4 minus 3, that's just 1. So we have a e to the 0.40, and then we've got 10 times by this, which is 10, and then, well, that's all we have for that term. So we add on 10b e to the 0.40, and then we've got 10 lots of this term minus 3 lots of this term. So we have 10 times 0.4 minus the 3, that's 1, so we have here bt e to the 0.4t. So that's how we do part C. Part D of the question: at the start of 2010 there were 5 bears and 20 fish on the island, and we have to use this information to find the number of bears predicted to be on the island in 2020. Well, if we know what A and B are, we can use that to find out the particular solution for X, and then from that find out how many bears there will be in 2020. And obviously from 2010 to 2020, that's 10 years. So what we know already, there's 10 bears in 2010. So if we look over here for what we have for X, which is bears, for part D of the question, you can see here we've got at time t equals 0, X is equal to 5. So with this we have a e to the 0 plus b times by 0 times by e to the 0 equals 5. So therefore a is equal to 5. And when t is equal to 0, we also know y is equal to 20. So if we take a look at y is, we've got a e to the 0 plus 10b e to the 0 plus b times by 0 times by e to the 0, this is equal to 20. We know here we get 5, and then we've got 10b, this is equal to 20, b is equal to 1.5. And knowing what a and b are, we can therefore conclude that X is equal to 5 e to the 0.40 plus 1.5t e to the 0.4t. Okay, so let's call this equation 8, and let's call this equation 9. And we're finding out how many bears there will be in 2020, so that's when t equals 10. So when t equals 10, we've got X equaling 5e to the power of 4 plus 1.5 times by 10 times by e to the 4. So we need to work out what this is. So X is equal to, if we grab our calculator to do this, you can see here we've got 5 e to the power of 4, and then we've got 15 e to the power of 4. So it turns out we get a value approximately equal to 1092. Okay, so this is the number of bears in 2020. Okay, so that's how we approach part D of the question. And now for part E, we have to comment on the suitability of the model. So the model predicts the number of bears and the number of fish will grow without limit, so it is unlikely to be realistic. Example number 13. 2 barrels contain contaminated water. At time t seconds, the amount of contaminant in barrel A is x milliliters and the amount of contaminant in barrel B is Y milliliters. Additional contaminated water flows into barrel A at a rate of 5 milliliters per second. Contaminated water flows from barrel A to barrel B and from barrel B to barrel A through 2 connecting hoses and drains out of barrel A to leave the system completely. The system is modelled using the differential equations dx over dt equals 5 plus 4 over 9y minus a 7th x. That's equation 1. And we've got dy over dt equaling 3 over 70x minus 4 over 9y. That's equation 2. We have to show that 630 lots of d squared y over dt squared plus 370 dy over dt plus 28y equals 135. And what you'll notice here, there's nothing involving x. We've only got the variables y and t. So we need to eliminate everything involving an x. So if you take a look at equation 2, we can rearrange that. So we have dy over dt plus 4 over 9y equals 3 over 70x. And from this we can find out what x is. X is going to equal 7 over 3 dy over dt plus 280 over 27 lots of y. And now we need to differentiate both sides with respect to t implicitly. So we've got dx over dt equaling 70 over 3 times d squared y over dt squared plus 280 over 27 dy over dt. So we'll call this equation 3 and we'll call this equation 4. So now what we need to do is substitute in equation 3 and equation 4 into equation number 1, which will eliminate everything involving an x. So if we do that, we have dx over dt over here, which is what we've just found here. So we've got 70 over 3 d squared y over dt squared plus 280 over 27 dy over dt, and this is equal to 5 plus 4 over 9y, and then we've got minus 1/7 x, so we've got minus 1/7 lots of 70 over 3 dy over dt plus 280 over 27 y. So let's multiply through by 3. So if we times through by 3, we end up with 70 d squared y over dt squared plus 280 over 9 dy over dt. This is equal to 15 plus 4 over 3 y. And what we'll also do is multiply through by the 7th over here. So here we're going to have 10 over 3 times by 3, so that will be 10. So we've got minus 10 dy over dt, and here we've got 40 over 27 times by 3, which is minus 40 over 9 y. So if we now multiply through by 9, okay, so now multiplying through by 9, we have 630 d squared y over dt squared plus 370 dy over dt. Sorry, plus 280. Just reading ahead there. So we've got 280 dy over dt. This is equal to 135 plus 12y minus 90 lots of dy over dt minus 40y. And putting all this into the required form, which we see over here, hopefully here you can see we've got 630 d squared y over dt squared plus 370 dy over dt plus 28y. This is equal to 135 as required.